Thank you. We are going to talk about distributed data processing, and it's a library I am working on for about last 6 months. So just a little bit about me. About 5 years ago, I was working in Turkey at a startup called Apache Security, where we were developing a distributed Haskell application. While working there, I learned how to get multiple Haskell processes talking with each other to achieve a goal. And then about 3 years ago, I moved to New Zealand to work on a company called Movio, which is a company which processes large amounts of cinema-related data to get insights for moviegoers. So we have decent amount of data. We have billions of transactions, and we have millions of users performing those transactions. And working there taught me about large-scale data processing, and especially it taught me that the techniques we use to do large-scale data analytics are the same ones we are using in functional programming, right? We use higher-order functions, we use laziness, we use generics and things like that. So naturally, I thought Haskell would be a great fit to do large-scale data analytics, but I couldn't find any ready-to-use solution, so I tried to build one. So let's start by thinking when we should do distributed data processing. So it's a pretty big hammer, so you shouldn't use it for every problem you have. You should only use it when you have a really large amounts of data. So if your data fits in a single computer, or if your data fits in a memory, just write a simple application to process it. It will be much nicer. Or if your data is big, but you are only going to do some simple queries or simple transformations, it is much better if you use a relational database, and if you create a few indexes, it can give you your result in less than a second, so which will be perfect for you. However, if you have very large amount of very large amount of data, and you want to perform really complex queries and transformations, distributed data processing can work for you. So you can use it then. So the most widely used framework to do distributed data processing is Apache Spark, and the core data structure behind it is called a resilient distributed dataset. A dataset is a collection of rows, and those rows does not have any defined ordering, so it's like a set, but it can contain duplicates, so it's a multiset. But the trick is that instead of storing this dataset as a single entity, we store them as many separate partitions that can be fetched independently of each other. This gives us the ability to process those partitions in parallel on many different machines, and those machines are called executors, and hence we have our speed up. And since we have those hundreds of machines, something has to coordinate them. So we have another machine called driver, which actually knows about our code and coordinates those executors to process those partitions. However, when you have a piece of data you want to process, you really don't want to deal with all those executors and partitions and concurrency. Instead, those frameworks provide you a set of primitives, set of high-level combinators that we know from functional programming, like maps and filters and group bys and reduce functions, so that when end user wants to transform a piece of data, he doesn't need to know about the machinery behind it, and he or she can express the transformation using the high-level combinators. So distributed dataset is the name of the library I'm developing, and it's written in Haskell. It borrows a lot of ideas from Apache Spark, all the ideas I mentioned before, and And the API is pretty much like Apache Spark, but the underlying implementation is quite different. So the objective is not to be a clone of Apache Spark, but to be in the same space. A few differences than Apache Spark. The first one is that I designed it to compose nicely with the Haskell ecosystem. So distributed dataset does not come batteries included. It doesn't support many different data formats, or it doesn't support many different compression algorithms. But what it does is that if you can find a library to do those in Hackage, it only takes 1 or 2 lines of code to add it to distributed dataset. So you can just plug in the parts you want from anywhere. Another difference is that I designed the library to play nicely on this new function as a service, or aka serverless offerings from various cloud services. And it provides a few nice benefits that I'm going to talk about later. Let's talk about how it is actually implemented. So the first obstacle I faced when implementing this was about sharing a computation, sharing a Haskell function across different machines. So if we were using an interpreted language, or if we were using a language with a portable bytecode like Erlang or Java, it is relatively easy to distribute a computation. We can distribute the portable bytecode, or we can distribute the code itself, and on the remote machine we can evaluate it. However, in Haskell, it's not that easy. When you compile a Haskell executable, there is no way to convert a function to a byte string, send it across the network, and convert it back to the function. However, this problem is solved by the Cloud Haskell project, where instead of sending the functions themselves, they assign a unique ID to those functions and communicate using those unique IDs. And the Haskell compiler GHC added a support for it in the name of StaticPointers. And using that, if you have an expression, if you use the static keyword, if you put the static keyword in front of that expression, GHC will add that expression to a table embedded in your executable and return you a ID called StaticPointer that refers to that. And that ID can be sent across the network. And if you are using the same executable on the remote machine, you can get back your original function. So this is exactly what I wanted, except for one thing, where I wanted those static pointers to compose with each other. So when you have multiple static pointers, I want to be able to combine them together to get bigger and bigger computations. But static pointers by itself does not provide this ability. However, there is a library in Hackage called distributed closure, which provides you an algebraic data type on top of static pointers, and it gives you the ability to compose those static pointers with other static pointers, or with runtime values if they are serializable. So when you have this closure data type, then you can express almost any computation you want, and you can send them across the network. Turns out, once you have this ability to have composable serializable functions, building a data processing framework on top is not that hard. The first thing you need is a definition of a partition. So in this framework, a partition is just a conduit which produces values of any type. If you are not familiar with the Haskell ecosystem, a conduit is something like a stream processor. So whenever you see conduit A, B, it means that it's a stream processor which can take many A's and yield many B's. So a partition is just a stream processor which produces A's. And since it's a closure, it means that I can send it across the network and run it on remote executors. So a dataset is a data type with multiple constructors, and the first one is called d-external. This d-external is the only way to create a dataset from scratch, where you can provide a bunch of partitions and it will give you back a dataset. And this is how you integrate your existing data to distributed dataset. However, once you have a dataset, distributed dataset gives you the ability to transform those with this combinator called dpipe. A dpipe tells you that if you have a conduit from A to B, then I can convert a dataset of A to a dataset of B. And how it does that is that it sends the conduit to those hundreds of executors, passes every partition through those conduits, and calls the resulting set of partitions a new dataset. So as you can imagine, once you have this combinator, you can implement things like maps and filters quite easy by just passing different conduits. However, there are some transformations you cannot express, and those are the transformations which uses information from multiple input rows to give the output row. For example, let's say that you wanted to implement something which deduplicates the rows in a dataset. What we can do is that we can use this dpipe constructor to deduplicate rows within a partition. However, that doesn't give us the result we want because there can still be duplicates across different partitions. So what we need to do is that somehow we need to change the partition structure so that the relevant rows are in the same partition, and the departition combinator does that. What it says is that if you give me a key function and a dataset, I can give you another dataset with the same type. But the difference is that the returning dataset has this invariant that every row sharing the same key according to this key function will be on the same partition in the end. So now with this combinator, what I can do is that I can first call departition to make sure that every row with the same value to be on the same partition, and then I call my dpipe function to deduplicate, to remove the duplicates. And after that, I know that there is no duplicates. So it turns out just having those functions is enough to express everything Apache Spark can express. And there is just one more type I added on top to make things a bit nicer, and it's called an aggregation. So it turns out when you are dealing large amount of data, aggregating it is quite useful because you want to make it smaller so that you can understand what's going on. So an aggregation is something which combines many A's to a single B, and it also runs in this massively parallel fashion. So what it does is that it first aggregates every partition within itself and repartition it, and then aggregates those results. And turns out this concept is pretty familiar in Haskell and represented as a monoid. If your rows are monoids, then you can concatenate every partition and then concatenate the results, and it is exactly the same as concatenating every value sequentially. And the reason is that monoids are associative, so it doesn't matter in which order you do your combinations. So this aggregate from monoid function says that if you give me a proof that something is a monoid, then I can return you an aggregation that does the concatenation. And so once you have an aggregation, what you can do is that you can either apply it to the whole data set and get a value back, or you can apply it to the rows sharing a specific key, so that you can answer to queries like what is my yearly income for the last 6 years, or things like that. Another thing to mention is that those aggregations are applicatives and profunctors. It means that you can combine smaller aggregations together to create bigger and bigger aggregations, and you can manipulate the input and output type of an aggregation so that they can work on different inputs. Up until now, I talked about how how the transformations are expressed, but now I'm going to talk about how they are actually executed. Distributed dataset uses something called a backend to actually run the executors. Those backends are provided as external libraries. So if you don't like the ones provided by me, you are free to implement it as an external library, and distributed dataset will work with it. The first backend implemented is called local process backend, which uses local processes to process the data and use the local file system to exchange information. As you can imagine, it's not really useful because it doesn't give you any speed up, but it's really useful when you are writing your unit tests or when you are developing the application. But a more exciting backend is called distributed dataset AWS, where it uses AWS Lambda to run executors, which means that without requiring any infrastructure, you can run thousands of executors in seconds, which is perfect for our use case because that's what we want. We want to use thousands of containers in a really short time to get our results faster. And another thing is that, as I said, it doesn't require any infrastructure. So if you only have your AWS credentials on an empty AWS account, this backend will work. So since we have everything ready to run those, to do the aggregations, let's look at an example. So this example is, the objective of this toy example is finding the GitHub users who use the word cabal in their commit messages the most. So first thing we are doing is that I'm using this gharchive function, which returns me a dataset of events from GitHub. And I'm using it to fetch every public GitHub event happened on 2018. So it's like relatively large amount of data. First thing I do is that I take this event, I extract the event author, and then if that event is a push event, I get the commits and get the commit messages, and I create nice tuples. At this point, I have a data set of a tuple where the first element is a GitHub user and second element is a commit message. I filter the commits if they contain the word cabal and case insensitively. And next, what I do is that I use the grouped aggregation function to group them by GitHub users and count how many commits they have. And after this, I have a data set of a tuple where the first element is a GitHub user and the second element is the number of times they use the word cabal in their commit messages. And then I run one more aggregation to get the top 20. This aggregation fetches the results to the driver so that I can print them to screen. A few things I want to mention. As you can see, all the transformations we defined is just ordinary Haskell functions using ordinary Haskell types, and you can use any package library you want. So I use lenses and I use text library. And another thing is that this looks, at least to me, this looks like this looks pretty natural. It isn't like a weird DSL with strange operators. So when you run this code, it is going to download about 130 gigabytes of data from gharchive. It is going to decompress it, and it will result in almost a terabyte of JSON. It is going to use about 2,000 executors to process this data in parallel, like do the downloads and extraction and all those transformations. And the computation will finish in less than 2 minutes, including the time to send our binary to cloud and start all the containers and etc. Another thing to mention is that even if we were to use a much bigger data set, like GitHub events for the last 10 years or something like that, our execution time wouldn't increase that much. Only thing that will happen is that we are going to use more executors and spend more money, and execution time will increase, but not linear to the data size. So pretty much this is everything distributed datasets can do. But it is not the only library in Hackage to do those things. The first one and the most famous one is Sparkle. It's a library. It is developed by Twig.io. What it does is that it wraps Apache Spark and lets you write transformations in Haskell, but in the end runs them using the Apache Spark. The advantage is that it supports everything Apache Spark supports easily. The disadvantage is that it's a bit more complex because now you have a Haskell executable embedded in a jar where there's like JVM and Haskell runtime system, and they communicate with each other, and you use those massive softwares like Hadoop and Spark. So it's a bit more complex. Another one is called HSpark. HSpark is a port of Apache Spark to Haskell using distributed process. So it's pretty similar to what I'm doing. The main differences are it is much more faithful to what Spark is. So the data types they are using and the way it uses executors are pretty similar. And also it doesn't have any commits on the last 4 years, I think, so it's not really maintained. So this is pretty much all I wanted to talk about. If you want to use the library, read the source code, like create issues and send PRs, this is the GitHub URL. I really appreciate if somebody uses it and actually provides me some feedback, because currently I'm the only one who ever used it. And here's my email address if you need to ask anything or like if you have a comment. Yeah, thank you very much for listening, and I hope you find it interesting.
Awesome. Thank you very much.